In this video, we're going to talk about the 2011 AP Calculus AB free response question number 4. In the first part, we're just going to talk about part A. So here we have a continuous function, excuse me, a continuous function f. Very important on the AP Calculus exam to notice what they're giving you the graph of. So this is the graph of f here. Defined on the interval from -4 to 3 inclusive. 2 quarter circles and 1 line segment, as shown above. And then g of x is equal to 2x plus the definite integral from 0 to x of f of t dt. For part A, we're supposed to find g of -3. So g of -3 is the first thing we have to do here. G of -3 would equal 2 times -3 plus the definite integral from 0 to -3 of f of t dt. Well, the first part is obviously just -6, 2 times -3, so that's easy. And for the second part, evaluating this integral, we just have to recognize, well, two things. First of all, that the definite integral is just the area under the curve. So we're looking for the area of this quarter circle up here. This is the area that we want. And because they told us that it is a quarter circle, we know, of course, that the area is going to be pi r squared over 4. And the radius, we can see, again, if it's a quarter circle, then the origin is the center, and so the radius is 3. So, pi times 3 squared over 4, which is 9 pi over 4. So the first thing we had to recognize was, one, this definite integral is just the area under the curve, and that it's a quarter circle. But then we have to be careful because this is the integral from 0 to -3. And normally we do the integral from the smaller number to the bigger number. This time we're going backwards, which essentially means that for my area, all the lengths are negative. So we have negative lengths times positive heights, which means we have negative area here. So this is actually going to be -6 minus 9 pi over 4. For the first part here of the answer. -6 minus 9 pi over 4. That's g of -3. Then we want to find g prime of x. Well, g prime of x, it's a sum of two different things, g of x is. So we just need to differentiate each of those things separately. The derivative of 2x is just 2, and then the derivative of the antiderivative is just the original function. So then this is going to be plus f of x. And that's just sort of the fundamental theorem of calculus there. Derivatives and antiderivatives undo each other. So that's g prime of x, and then g prime of -3, g prime of -3 would equal 2 plus f of -3. F of -3 is just the value of the graph here at -3. So when we go to -3 on the x, we see that the value here is 0. So this is 2 plus 0, which is 2. So now we have answered all three parts. We found g of -3 was -6 minus 9 pi over 4. No need to try to simplify it any further than that. G prime of x was 2 plus f of x, and then g prime of -3 was 2. And that's part A. Let's move on to part B. In part B, we want to find the x-coordinate of the point at which g has an absolute maximum on the interval, and then of course justify our answer. Make sure you read the directions carefully. Whenever they ask you to justify, include a justification or an explanation. We know that typically, to find an absolute maximum, you want to find the derivative and find the critical numbers. So in the last part, part A, we said that g prime of x was equal to 2 plus f of x. And then to find the critical numbers, we take that derivative, set it equal to 0. 0 is equal to 2 plus f of x. Solve this, and we're basically looking for where is f of x equal to negative 2. So, when we look at the graph, we can see that negative 2, right there. Now, it looks like that's going to be somewhere between at x equals 2 and x equals 3. We can tell, though, because this is a straight line here, the second part, they tell us that's a line segment. And if you just look at it and figure out the slope, you can tell that that equation is actually y. Oops. Y is equal to negative 2x plus 3. So just to double check, we want y to equal negative 2. So we solve this, put negative 2 in for y, and solve for the x. When you do that, you'll get 2.5 for your x. So I know that that's my only critical number. So I have a critical number when x is equal to 2.5. Critical number. And then I know that I'll have a maximum, a relative maximum, if the derivative changes from positive to negative at that point. So if we just test real quick, we can look at g prime of 0, which would equal 2 plus f of 0, which is going to be 2 plus 3, which is 5, which is greater than 0. And then look at something on the other side of 2.5. So we'll look at g prime of 3, which is again going to be 2 plus f of 3. And f of 3 is negative 3, so this is 2 plus negative 3, which is negative 1, which is obviously less than 0. So the x-coordinate that we're looking for is the 2.5, and we can say g has a maximum at 2.5. So g has a max at 2.5 because g prime changes from positive to negative at x equals 2.5. So that's kind of my justification there, and that would be my answer right here. It should be noted that when we're talking about an absolute maximum, we also want to double check that the endpoints are not the maximum value, but it's fairly obvious that negative 4 is not going to give us the maximum. Negative 4, if we plug that in, we get negative 8, and then there's no, and then this is, again, it's going to be negative area from 0 to negative 4, so that's not going to be right. And then we actually already tested the other endpoint, which is g of 3, and that was negative 1, so that's not going to be a maximum either. So our maximum value is at 2.5. Now let's go on to part C. In this one, they want to find where does the graph of g have an inflection point, and then again give a reason. Just like finding the absolute maximum in the last one, we want to think about using derivatives. So we know that we have inflection points where the second derivative is 0. So in the last one, we had that the first derivative was 2 plus f of x. So then the second derivative, g double prime, Well, the derivative of 2 is 0, and then the derivative of f of x is f prime of x. So we just need to know where does the slope of f equal 0. That's what we're solving for. So we have inflection points occur where the second derivative is 0. If we look at the graph, though, there's nowhere on the open interval from -4 to 3 where we have a slope of 0. It looks like maybe close to -4, but -4 is not actually in the interval now because it's an open interval. Also, at 0, it looks like it was going to be approaching 0 slope, but it's not actually defined here, the derivative. We have a cusp. But that's okay because you can have critical numbers where the derivative is either 0 or undefined. So our critical number is x equals 0. So let's write that down. X equals 0 is a critical number. Number for the second derivative, g double prime of x. And now, just because you have a critical number, again, critical number being where the second derivative is either 0 or undefined, does not mean you have to have an inflection point. There actually has to be a change in the concavity. So just like in the last one, we need to test points to see if the derivative actually is, to see if the second derivative this time actually changes from positive to negative. And because f prime, there's no actual equation for f, we're just looking at the graph of f. This is the graph of f here. And we can see clearly that from on the left side of 0, when x is negative, we have positive slope the whole time. And then after that, we have negative slope the whole time. So clearly it does change sign, which means that g would change the direction of concavity. And that's kind of the trick in this one here, is that we're looking at f, and we're talking about g. Where is g concave up and concave down? So we have to recognize that I want to just do the second derivative test for inflection points. Take the second derivative of g, which is the first derivative of f. And then since it's the first derivative of f, I'm just looking at the slope of f. Positive slope, undefined, so my critical number, negative slope. I've changed my sign, which means that on the original g, which I don't have a picture of, it does change concavity. So, a reason for my answer, x equals 0 is my critical point and my inflection point. So let's say g has an inflection point at x equals 0 because g double prime changes from positive to negative at x equals 0. That would be my answer. And it's just, for my justification or giving a reason, it's just exactly how we think about the problem. How did I test? Well, I checked to see where the second derivative changes from positive to negative. I don't need to say anything more than that. So g has an inflection point at x equals 0 because g double prime changes from positive to negative at x equals 0. And that's all I need to say. One more part D. Let's do it. Part D says find the average rate of change of f on the interval from -4 to 3. And then they say there is no point C on that open interval from -4 to 3 for which f prime of C is equal to that average rate of change. Explain why this statement does not contradict the mean value theorem. Let's deal with this two parts at a time. First, find the average rate of change, and then we'll do the whole C thing. So the average rate of change, and this is really important, the average rate of change, we don't want to confuse that with the average value. we're looking for the average slope. And average rate of change, or average slope, is just your normal slope equation for the two endpoints. So for part D here, what we're going to do is we're just going to take f of 3 minus f of negative 4 over 3 minus negative 4. Just slope. Slope between the endpoints. What is the average rate of change? It's what you would have done before you knew calculus. Calculus told you how to find instantaneous rate of change. Now we're going backwards and we're just doing average rate of change. So f of 3 is negative 3. F of negative 4 is negative 1. So that's going to be minus a negative 1 plus 1. And then 3 minus negative 4 is 3 plus 4, which is 7. So then we get negative 2/7. And that's our average rate of change. So that is our average rate of change. First part of part D, done. Now they go on and talk about this point C thing and the mean value theorem. What the mean value theorem says is that when you calculate the average rate of change, which we just did and we just said is just the linear slope between the two endpoints. What the mean value theorem says is there has to be a point C in that open interval such that the instantaneous rate of change, the derivative, is the same as that average rate of change. Unless the function is not continuous and differentiable on the interval. So, because we already talked about in the last one, we're not differentiable here. We have a cusp, the derivative is undefined. That means the mean value theorem does not apply. So, they say, explain why this statement does not contradict the mean value theorem. Say, the MVT, mean value theorem, was not contradicted because f is not differentiable at x equals 0. The MVT was not contradicted because f is not differentiable. Sorry, my handwriting is terrible in this one. The MVT was not contradicted because f is not differentiable at x equals 0. And that's all we really need to say. I'll say one more thing. Just be very careful. They love to ask this question about the average rate of change, and people get it confused with the average value, which average value means you have to take that, you have to do, let's just write it down, average value. This is kind of just on the side here. It's 1 over b minus a times the integral from a to b of f of x dx. That's different than average rate of change. Now, one thing that you could do if you wanted to is you could say, well, the average rate of change is finding the average value of the derivative. You could do that, but generally I think it's easier if you just remember to keep them straight. Average value is one thing, average rate of change is another. Average rate of change is just the slope between the two endpoints. So be careful, remember that. Always read the question carefully. In this question 4, sometimes they're talking about f, which we have graphed, other times they're talking about g, which is this integral in terms of f. So be careful. Alright, thanks for watching.